Can everybody hear me? Sounds like the audio's up now. Great. Thank you very much. It's wonderful to be here. I am Bob Rogers. I am Chief Data Scientist for Big Data Solutions at Intel. And my mission is to put powerful analytics in the hands of every decision maker. So today you're in for a treat because I'm really just here to set up Durga from AOL, who will show you some amazing uses of AWS that they've done where they're actually distributing their distributed analytics. Extremely cool. And so I'll set things up here for the first 20, 30 minutes or so and talk about my own perspective on big data and where Intel fits in, and a little bit about big data analytics from the point of view of looking at different types of data, particularly unstructured. So, why am I here? Well, this is my background, Chief Data Scientist for Big Data at Intel. I started my career as a PhD astrophysicist, and I was interested in computer models of stuff falling into supermassive black holes. And so, partway through my postdoc research, I got interested in computing the way the brain computes. So that resulted in some research, including writing a book on time series forecasting with artificial neural networks, computing the way the brain computes. So anyone want to take a guess at, people started calling me, and they wanted to know, Bob, can your models forecast? Anyone want to guess what it was? Stock prices, exactly. Can your models forecast the stock market? So I didn't know, so I started a company, and I found out that I could. So for 12 years, I ran a quantitative futures trading program. That was really my first introduction to big data analytics because I had a 2 gigabyte, just think about that for a second, 2 whole gigabytes of data, tick-by-tick data on the futures markets. This was in 1991. And so actually in 1991, 2 gigabytes of data was not easy to work with. And so with some decent algorithms and a 7-foot-tall guy in the futures pit in Chicago actually doing the order filling, I was able to have very good performance for 12 years. In 2006, the world had changed a little bit. 2 gigs of data was not big. The algorithms were not necessarily as cutting edge. The 7-foot-tall guy in the pit was actually replaced by the shortest piece of optic fiber that you could get between you and the electronic exchange. So I was ready to move on. I became a product manager for a global medical device called the Humphrey Field Analyzer, and that was extremely interesting. Helped me learn about healthcare, which paid big dividends in 2009 when the US government started incentivizing doctors to use electronic health records. Okay, so the idea was, here in the US, our healthcare is twice as expensive per person than anywhere in the developed world, yet when you look at our quality measures and the standards of care, they're certainly no better. In many cases, they're not as good. So the idea was get the data electronic, we can all relate to that, and then use that to optimize the health system, improve care delivery, improve outcomes. It's going to be a happy ending. So in 2009, I formed a company called Apixio to use big data analytics to analyze all the data that was going to be coming out of these systems. And so I'll talk to you a little bit about that because that was an application of variety in big data. So has everybody heard of the 3 V's of big data? Raise your hand if you have heard of the 3 V's. Okay, so volume, which is the idea that big data analytics comes into play when you have lots of data to deal with. Some amount of data that's hard to deal with the biggest server you can think of. Okay, so that's your volume. You have, second V is velocity. Your data is coming in at high speed. You've got either very, very low latencies or just a whole bunch of data coming in fast, and you need to get good turnaround times. And then finally, variety. So in many cases, we've been very comfortable doing analytics on structured data, relational databases, anything that's rectangular in shape, that we kind of know what's there, right? But we humans do not generate structured data. I'm generating unstructured data right now, right? So the ability to analyze unstructured data is a critical part of your big data analytics story, and it's a huge opportunity for many of us in analytics. Okay, so I'll talk a little bit more about that and set up the variety side of things, and then Durga is going to talk to you about volume and velocity and what they've done at AOL. So fast forward 5 years, Apixio is doing fine. Intel came to me and said, data is the new currency, and we need someone to come in and help us just think about how can Intel continue to be a leader in computing and analytics, especially around data. So I was fortunate enough to join Intel last January as chief data scientist for big data, and it's been a fantastic ride. This is not an advertisement for Intel, but Intel is a wonderful company to be associated with. So why big data at Intel? Don't we just sell chips? And the answer is yes, we do sell chips. Many of our chips go into servers, and we want our customers who are using our chips in their data centers to be as successful as possible. So Intel spends a huge amount of effort actually optimizing the software and the hardware to help our customers be successful. We do a lot of work helping our customers do well with their analytics, because if they do well with their analytics, they're going to invest in their data centers, and it works out well for everybody. It's a win-win situation. So on the far left, you have the Internet of Things, one of Intel's major efforts. You have computing in sensors, you have computing in gateways, you have computing in the data center. So it's an end-to-end set of solutions that take data from out here where we've got our wearables and our industrial Internet of Things devices, pulling the data all the way into the data center. So that's a big area of investment and interest for Intel. On the right-hand side, I have my picture of DNA, and it says optimization. So what's that all about? Almost every piece of software that you use commercially or that you use from open source has actually been optimized by Intel engineers to make it run really, really well on Intel hardware. So that's a critical thing to understand. Your software, whatever you're using, is going to work well on Intel hardware because of the efforts that we've put in. The DNA is there because from my healthcare background, the optimization that I'm most excited about is the optimization of gene sequencing systems. So we've actually made it possible by working with the companies that create the analytics to do gene sequencing. We've actually sped up the process by 1,000x. So what used to take days or weeks to sequence a patient can now be done in hours. And that is, just from a technical point of view, that's really cool. But actually, from a life-saving point of view, it turns out that patients with cancer, for example, have mutations that occur during the course of their disease. And if you're able to sequence at high enough speed, you can actually track the progression of the disease and proactively target with your therapies to save those patients' lives. And so we're working with healthcare organizations and research institutions to actually take this high-speed gene sequencing and put it into production in the clinical workflow. I can't imagine doing anything more exciting than that. So that's that. Now, finally, in the center, we have open source. So Intel believes strongly that open source is a critical part of our entire analytics ecosystem. So we are the top 2 contributors to Linux every week, top 3 contributors to Spark. We contribute directly to the Hadoop Apache trunk and also to Hadoop via Cloudera. which is a partner of ours. So we're putting a lot of effort into enabling the analytics ecosystem through our open source efforts. And then just in the last week, actually just last week, we announced in New York City at Strata Hadoop, the Trusted Analytics Platform, or TAP, which is an open source project that takes a foundation that can either run in AWS or can run on-prem. It integrates data science and data science tools with app development and deployment. So it's collaborative because it allows data scientists to build models that can then be exposed as services for app developers to pick up and deploy. It is flexible because it is actually built to take in libraries and tool sets that data scientists use already, bring them into the platform and be able to leverage this collaborative capability. And it builds a community not only because it's open source so that developers can pick up the ball and run with it in ways that we didn't even imagine, but because it creates a space where data scientists can work together, they can work with app developers, and so we get an exponential growth of our ability to actually create with data. So it's a very exciting step forward in open source, and you can go by the Intel booth and talk to people about that. There's a display showing some of the applications that have been built. I think it's very exciting. To focus more on AWS and what Durga is going to talk about, we have some specific areas that we've made contributions to the Apache Hadoop source code. So in particular, we've done a lot of feature development and optimization for HDFS itself around remote procedure calls, optimization around Pig, also quite a lot of just debugging for those of you who have worked with Pig. We have put some new features around Hive on Spark and Hive in general so that, and this is important for enterprise development, enterprise always needs to have a way to run SQL on top of its big data stack. And so there's a number of different ways to do that, and Intel's working hard to make sure that those are available and that they're robust. And then the lower right, encryption, we've actually, based on chip level encryption through AES-NI, encryption is 17 times faster than it was before. So for encrypting your data in your Hadoop stack, you can actually now encrypt all of your data with only a few % overhead, which means that you don't have the risk of, gee, which parts of my pipeline am I going to encrypt? And oh, did we spill something on the floor and accidentally get a breach? There's a lot of risks that get taken out of the equation when you're able to encrypt at high speed across your entire system with very little overhead. So I think that's very exciting coming from healthcare, where security is just absolutely critical. It's a real benefit for the platform. So I'm going to pause there for a second, and I'm actually curious about all of you. I told you about my history, but what about you? Raise your hand if you are an actual app developer or coder. Okay, about maybe a fifth. How about IT or development managers? Okay, another fifth. Decision makers for analytics or IT? Okay, another sixth. Who didn't I get? I know you're out there. I got everybody. Okay, so we're all app developers, IT managers, and decision makers. Okay, great. So, what I want to talk about now is the use case that I developed when I was at Apixio about the variety part of big data, okay? So, as I said, we took we're looking at the data from the healthcare system. Doctors were incentivized to use electronic medical records, and the idea was we put all the data together, and all of a sudden, we know what we need to know about patients. If we know what we need to know about patients, we can optimize the health system, right? So, anybody been to a doctor and the doctor didn't know something they should have known about you? Few people, okay. It certainly has happened to me. So the use case that I'll talk about is taking all of a patient's clinical data, their structured data, and in particularly their problem list. This is the list that your clinical decision support or your provider uses to know what you have in your history and what problems you currently have. We're going to assemble that, and we're just going to measure the false negatives. This was an actual problem that we solved, and the idea was once we've pulled all this data from all these different sources, we're going to know the answer. So here's the part, you know that I'm a technical guy, so we need to talk about what does a patient look like to a data scientist. Okay, so this is what the patient looks like. They've been de-identified for HIPAA purposes. And so they have a number of different data sources coming in, right? So we have a doctor up on the upper left entering information into the clinical record. We have data coming from a basis watch, which is tracking sleep and heart rate and things like that. We have data coming from a different source. It's a hospital where the patient was seen on an emergency basis. All these different sources of data need to be brought together. So the idea was you bring it together and you're going to get the full story. So this is a problem list from one source. You can see there are just a number of conditions listed, things like headache, hypertension, et cetera. We've got another source of data. It's coded in a particular coding system, that's ICD-9. It's what the doctors use to put in your diagnoses to get paid. And we'll take a third source. Imagine bringing these together and simply aggregating. That was the initial premise of what we did. And so the question is, when we measured our KPI, that is the false negatives in the problem list, what do we think we got? So I'm going to ask right now, based on your experience with healthcare, what % of the key clinical information that your doctor should always know about you was missing from that aggregated view? 0 to 25%? Anybody? Boy, no takers. It's a lot of doubters in the room. How about 25 to 50%? Okay, now we're getting some maybe a quarter. 50 to 75% missing? Okay, and what about 75 and above? Okay, those are the doctors in the room. They always tell me, oh yeah, none of that data is usable. Okay, so the answer turned out to be 63% in our study. So 2/3 of what your doctor should know about you is missing from their structured data, even after combining all the data across the entire system. That was shocking to me. So where did the data go? I mean, what's going on here? Doctors don't, I mean, there are problems, but they don't kill us every day. So what happens? Well, this is an actual patient's chart, aggregated. The top section is their problem list, structured from all the different sources. You can see there's a few things listed there. The next one down I've highlighted, this is the primary care doctor's notes. And they typed hypertension. Never put it in the problem list. It never showed up anywhere coded, but they did note to themselves hypertension. The smoking gun is the last one. That is actually a scanned document sent to the primary care doctor from the cardiologist. And if you read it, ironically it says, you are aware of his acute myocardial infarction, which is a heart attack, 4 years ago, et cetera, et cetera. So the cardiologist thinks that the primary care doc knows that this is part of this patient's history. They've had a heart attack. but it's nowhere else in the chart. It's not in the structured data, it's nowhere. So this is where the big data analytics finally comes. And thank you for bearing with me to get to this point. So the question is, how do we do analytics on a system where the structured data is missing 63% of what we need to know? Well, the answer is we analyze the text. And in this case, that's our variety of data in the big data world. We need a system that will allow us to analyze unstructured data. This is a problem that we're all going to face in our analytics careers or in our development careers, because so much of the interesting data in our world, whether it's call center logs, internet, blogging, reviews, clinical notes, is unstructured, that these analytic systems are incredibly important. So, and actually, the doctors in the room always giggle when they see the coffee stain, because they all know they did that. Okay, so this is the stuff we're looking for: congestive heart failure, hyperparathyroidism. That's the stuff we need to pull out of the text. So what we did at Apixio is we built a data platform, an analytics pipeline on AWS, and that's where the encryption came in, because to be HIPAA compliant requires us to make sure everything's encrypted all the time. AWS was a perfectly excellent platform for that for us. We were able to build a scalable pipeline that took the data for these patients, all the text, all the images, OCR the images. There's a step in the pipeline that identifies whether the image should be OCR'd. There's another step in the pipeline that uses machine learning to determine, is this a clinical document or is this some sort of lab form, or if it says diabetes on a lab form and it's not checked, you don't want to include that in the patient's analysis, right? So this pipeline took these unstructured pieces of data along with the structured data, put them through a number of steps, including OCR, including text analytics, and in particular, text mining, not deep NLP, but text mining. It's an important point to understand what's in the text. So the reason I underscore text mining as opposed to natural language processing is that if you look up natural language processing, has anyone done natural language here? Yeah, a few. So those of you who have done it will recognize that there are some very deep and computationally intensive components to natural language processing, which may or may not add value to your process. So what we did is we actually started with text mining, looking for the things that were most important. And then we did a shallow parse to understand whether, when it says diabetes, is it preceded with no evidence of? Those are two different answers. So, but it doesn't require deep natural language processing. So the point is, it was a pipeline that used a number of elemental, simple analyses, but put together into a complete scalable big data environment. We were able to scale up and down the number of nodes that we used for the computation to generate our summary of each patient so that we knew what they had. And that was all done in AWS. The typical customer that we had would have 100 million documents to analyze this way. And then billions of measurements, labs, structured values, some of which were reliable and some of which weren't. So putting that all together and creating something computable was the output of that scalable pipeline, and it ended up being extremely successful. So, to summarize my experience before we hear Durga's really amazing, very specific best practices, and you're really going to come away with some clear examples of what to do and what not to do, and what the world of possibilities is on AWS. Start with what you know. So we started with the structured data. We thought we knew that if you added it would work out, but it didn't. However, we'd measured the false negative number before and after. We knew we needed to do more work, and we just added one more layer of complexity, which was text mining in the text documents. That actually got us 95% of the way there. Huge advance, just starting with something simple and layering in one source of data. Second, leverage the existing technologies that you already have. So again, Durga will talk a lot about that. But there are a lot of tools that you're probably already using that if you assemble them into a scalable environment, you can actually take advantage of. Along the same lines, use the simplest tools. So we didn't go straight to natural language. We started with text mining because that gave us a lot of information without a lot of investment. Really important, because then we knew where to focus. And then finally, and I feel bad even saying this, but measure your results. Have a KPI, something that you measure beforehand. In this case, it was the false negatives in the problem list. You have to have a measure, because at the end of the day, there was a Gartner report recently that said 28% of executive respondents said that their big data projects were not necessarily successful. They didn't say they failed, but they said they were not necessarily successful. Why? In most cases, if you dig in, it's because they didn't measure something and clearly show that they had moved the needle. So when you're embarking on these projects, think about one simple thing that you can measure and show that you've moved the needle. There's a lot of collateral value that you're going to get, but you want to be able to show that one piece of advancement. So then, at the end of the day, you can use big data analytics to reveal what's hidden inside your data about your customers, your products, your entire business ecosystem, and eventually your opportunities. So I invite you to now listen to Durga's part, which Durga is a systems architect from AOL, and he's going to talk to you about velocity and volume in some really compelling terms. So thank you. Hey, Durga.
Hello, can you hear me? Thank you, Bob, for the introduction and for all the cues for my presentation. I've been talking to Bob over the last week or so, and there were so many synergies in the way we were doing things and how we can apply what we learned to any data set or any environment. So just to tell you about myself, my name is Jorgen Imani. I am a system architect at AOL. I design big data solutions for all of our traffic data and combining our traffic and advertising and audience data. I worked with Hadoop for the last 3 or 4 years and started working with AWS in the last 1.5 years. So at the beginning of last year, we had a challenge. We were processing a lot of our data in our Hadoop cluster in our data center, and it was about to go off lease, the hardware. So we had to make a decision what to do with the processes and data. And around the same time, we went for a training class for AWS, and we quickly realized that that is a natural solution for us. That was a very efficient solution for moving our application to AWS. What we did was we took the data that we were processing in our Hadoop cluster and uploaded it to AWS S3, and we launched an EMR cluster and processed the data using the EMR cluster and saved the output back on S3. We were using Hive and Pig for most of our data processing. And so it was relatively easy for us to take the code that we had in-house and put it on AWS because it's the same Apache Hadoop and Apache Hive versions that we were using, we could use on AWS EMR. And the data was saved on S3 and read and copied to the EMR's HDFS. and we applied the same Hive and Pig transformations that we were doing on the in-house Hadoop cluster, and the output was saved back on S3. Now, as you can see, we are still not completely in on AWS. We are in a hybrid mode at this point. We have a big database in-house that is used by all of our analysts and our reporting infrastructure to deliver a lot of reports to the executives. So in order to minimize the impact to our end users, we decided to first move all the data processing into the cloud and then tackle the other challenge later. So this is perfectly working for us. We extract the data from AWS and load it into our in-house database, in-data center database. So as Bob mentioned, the 3 V's of big data are volume, variety, and velocity. We definitely have multiple terabytes of data that we are processing. We get data in different formats. We get data in plain CSV files. We get Avro formatted data. We have JSON formatted data. All of that we are able to process in EMR in AWS. And the velocity, now I know for different people we have real-time and other near real-time data sources. For our use case, we predominantly have hourly and batch files that are arriving during the day at different times during the day. So one of the challenges that we had with the physical Hadoop cluster was we had the same Hadoop cluster on which we were running the hourly jobs, the daily jobs, the weekly jobs, and the monthly jobs. Now, all of them had different needs, different complexity, different data volume that it was processing, but all of them was being processed on the same physical Hadoop cluster. However, with cloud, we had the opportunity to essentially have a different Hadoop cluster for different purpose. So we have a Hadoop cluster with 2 to 5 nodes for processing our hourly data, and then we have a 100 to 150 node Hadoop cluster that we launch for our daily data. So how did we develop our architecture in AWS? We certainly didn't want to create one Hadoop cluster and have all of our data and processes run in that particular cluster. We tried that approach, we thought about it, and then we found out that we may be in the same situation where we may not be able to scale it fast enough to run different applications or different aggregations. So we took a different approach. We use S3 as our persistent storage engine, and we put all the data on S3. S3 acts as our input and as our output for all of our data. We spin up, as soon as we get the data that is ready to be processed, we spin up an EMR cluster and read the data, copy the data over to EMR HDFS, do all the transformations using Hive or Pig, and then write the output back to S3. Similarly, just to give you the nature of the scale that we do, we get 22 different data sets at an hourly granularity in hourly batches. So essentially we get 22 times 24 files every day. And each and every file is processed in its own EMR cluster. So at any point in the day, there are EMR clusters that are spinning up, reading the data, the corresponding input data, doing the transformations, and writing the output back to S3, and then at the end of the day, going away. There is no single persistent Hadoop cluster that is up and running all the time. This allowed us a great flexibility, as I'll explain in one of the use cases in the next few slides. The only two things that are always persistent are the S3 the data that we store on S3, and we have a cluster watchdog process which monitors all of our EMR Hadoop clusters. And if there is an error, then it alerts our operations team to look into the error and restart the process, or alert the development team for any data anomalies that may have arisen. So one of the things that made it really easy, as I have mentioned before, to move to AWS, to cloud, is we were using open source technologies. We were using Hive and Pig as our transformation coding engines, which essentially we took the same Pig script, the same Hive script that we had, and put it on AWS. We didn't have to change a thing. Everything ran as is, and that actually avoided a lot of recoding effort. And we use S3 and EMR and EC2 instances behind the EMR service. The other thing that we found useful was our data was in standard formats. We had delimited data, which was pretty common, and we have Avro and JSON data. And we could take the data as is and upload it to S3, and we could use the existing Hive or Pig scripts and process the data that was stored on S3. So keeping the data in open source data format and using open source programming tools to manipulate the data was definitely one big thing that helped us move quickly to the cloud with minimal recoding. Now everybody might be asking, you spin up 500 or 300 Hadoop clusters every day. Wouldn't that cost a lot of money? Well, one of the things we use is spot instances. As everybody knows, Amazon offers their excess capacity as spot instances for 1/10 the price of a regular EC2 instance. So because we were using all these transient EMR clusters, we could spin up an EMR cluster with all spot instances, do the process, shut it down. So you don't have to worry about my spot instances going away, my Hadoop cluster shutting down, because we were able to spin up a cluster, do all of our data processing, and shut it down within 1 hour. And that's where we spot the instances, we grab them, and we just don't leave them so easily. We actually squeeze the full worth of it. We just give it enough instances to finish the job in 59 minutes. As everybody knows, EMR EC2 charges are run by the hour. So there is no incentive for us to actually finish the job in less time. If we are finishing the job in less time, that means we are actually giving more than what we should be. So we actually take away a couple of instances to make sure that it does run for a full 59 minutes, unless there is a real reason for you to finish the data processing sooner. So the key feature, one of the key features, as you see here, that helped us scale and leverage all these cheap spot instances and separate is by separating our compute and storage. Now, we were able to store the data on S3, and we spin up different instances, different size clusters for doing different things. So, as I said, we have hourly clusters that process 1 hour's worth of data and finish that only need 2 to 5 nodes, whereas a daily job that processes more data and runs more complex aggregations needs 100 to 150 nodes. Transient clusters. So there is no single permanent cluster, and there are different size clusters for different data sets. Separation of duties. So we don't have a single entity doing all the processing or doing all the orchestration. We have independent jobs for processing the data, for extracting the data, for monitoring, and for loading the data. As you can see, we process the smallest chunk of data possible in a single EMR cluster. If you have data that is arriving every 15 minutes or every hour, separating it out and processing it in a parallel in a different environment will help you scale massively. So if there was a hiccup and you don't get the data for a few hours, but you get it all at the end of the day, we could still process all the data within 1 hour because we could spin up multiple EMR clusters in parallel. So one of the things that we had done is we have a unique use case of restating from time to time data that has been for the past 6 months because the business rules have changed, because some of the patterns in the data have changed, or they have identified patterns in the data and some of the aggregations need to be rerun on the existing data. So we had to do that from time to time. And this architecture helped us because we have 6 months worth of data that needs to be reprocessed and 3 different countries for which we had to process the data. So we had 180 days, essentially 180 days worth of data to be reprocessed. Because of the way we have separated out our data processing into different EMR clusters for every hour and every day, instead of doing all this reprocessing in one EMR cluster, we could launch one EMR cluster for every day in different availability zones. We, instead of doing it all in single availability zone where they may or may not be enough capacity, and with spot instances, you are actually bidding for excess capacity, and the more you bid in a single availability zone, the higher the price is going to jump up. So you will be competing against yourself. So we have designed the process to limit itself artificially by, as soon as there are 3,000 instances running in one availability zone under one account, under our account, we skip that availability zone and move on to a different availability zone and launch EMR clusters in that availability zone. And at one point, we had 550 EMR clusters running in 10 different availability zones. All of them finished the data processing within a few hours. So we were able to restate 180 days worth of data within a few hours. And since we use all spot instances, the cost of it was as low as it could be. And from the numbers that we have seen, we were able to save about 1/4 of the cost compared to a physical Hadoop cluster and AWS. So the facts that we have, the amount of data that we have approximately 150 terabytes of extremely compressed data. Because you are paying per gigabyte, it does help you to compress the data as well as possible, as much as possible. And we get 2 to 3 terabytes of raw data every day. And we launch 350 EMR clusters every day, processing all that data. And we have approximately 13 to 24 months of data that is retained on S3. This is the restatement use case that I was talking about, where we had 150 terabytes of raw data that was to be reprocessed, and we launched 550 EMR clusters in 10 availability zones with 24,000 active EC2 instances running at one point. So this is the AWS cost breakout. As you can see, in a physical environment or with a physical Hadoop cluster, it's not easy to get this breakdown. You don't know how much of the cost of the Hadoop cluster is for storage and how much is it for compute. Whereas with AWS, we could clearly see the cost of compute is definitely much more than the cost of storage of the data. It does also give us enough insight into what is the data set or the aggregation that is costing the most amount of money. And you can clearly identify whether or not that is important and relevant, and make a decision. And it helps and gives you that visibility and helps you make the decision. So some of the best practices and suggestions. Before I go into that, I just wanted to tie it back to how Bob's use case of clinical data and patient data. You might be wondering, like, okay, I'm talking about clickstream data, and Bob talked about patient data, healthcare data. If we have to design a solution for Bob's use case, think about having, rather than having one cluster, EMR cluster, that would process all the data that is coming through, you could have different EMR clusters processing different data. You could have one EMR cluster that is processing the structured data that is coming from multiple sources, and another EMR cluster that is processing the text documents that are coming through, doing OCR and taking that data and putting into an unstructured JSON or Avro format. And at the end of the day, if there is an analyst that has to analyze all this data combined, then he or she could run their own EMR cluster, maybe a 500 node EMR cluster, maybe a 1,000 node EMR cluster. They could spin up their own Hadoop cluster and run machine learning algorithms or natural language processing algorithms to process all this data and combine and gain some insights. So that's where my implementation can be used for any use case, any industry. By separating out the different data streams and using different technologies for different data streams. For the text documents, you would need some kind of OCR software, so you may or may not, you may need a different set of software that is installed on the EMR clusters. Whereas for natural language processing, you would need a different set of software like that would be installed on an EMR cluster. And depending upon the complexity of the analysis, you could scale the cluster up and down. By separating out these different processes, it can be very flexible, and you could still achieve your results without any capacity constraints. So coming back to the best practices and suggestions, one of the things that we found very useful was tagging. Tag all your resources with appropriate tags. We tag our EMR clusters, our EC2 instances, our S3 buckets with environment tags that tell us whether it's development, QA, or production. And this is useful not only for identifying whether a particular cluster is a production, development, or QA, but at the end of the month, when you see the bill and you want to know, why is my bill so high? What's costing me so much? Or what's the biggest chunk of the cost coming from? You get the breakdown in the bill by tags. So I could clearly see how much my development environment cost last month, how much my production environment cost last month, and how much my QA environment cost last month. And we could actually give you from a breakdown of costs for different environments down to the cost of a single EMR cluster. I could actually tell you how many cents my EMR cluster that processed this hourly data cost because of the tags that we have applied. So use tags as much as you can. The other thing is security. I'm sure security is a big thing on everybody's mind. So some of the things that we have done to enable or improve security for all of our data processing is we have defined IAM users for all the users in our account, and we have assigned specific roles for them. So we have defined roles that would restrict permissions. So we have a production operations role that has permission to read, write data to the production data buckets. We have development and QA roles that have permissions only to read dev and QA buckets. They cannot write anything to the production buckets. That way, a developer cannot accidentally go and erase any production data. So we have implemented all these restrictions, roles, and policies through AWS Identity and Access Management. And the other thing that we have done is we actually disabled access to all of our production EMR clusters. We do not enable any SSH access to our production EMR clusters, because when a step fails or a particular job fails in our EMR cluster, it shuts down, throws all the logs on S3, and the operations team doesn't have time to actually log in and see what's happening. They get that information from the logs. So there was no reason to enable access to the Hadoop cluster in production at all. So we disable all the SSH access to all of our EMR clusters. So that's the keyless EMR clusters that we're talking about. And other things are using Spot instances and infrastructure as code. There is no, all the code that actually launches an EMR cluster, all the configuration, everything is in the code that we have. So we could take that script and run it, and the script itself is in version control. So we don't have to worry about losing the configuration information for an EMR cluster. Some more best practices are listed here. I don't want to go through all of them, but some of the things that I think I would talk about for our use case was having a good naming convention. You know, in S3 have a hierarchical data structure of having a data set name and then separating out or partitioning the data by day, year, and month within the data set, so that people can clearly see what data set it is and how many years worth of data or how many months worth of data do we have for that particular data set. So having a good hierarchy and a good naming convention in S3 and tags are definitely going to help you. So the next steps, some of the next things that we would like to try, we are going to try in AWS are the database in the cloud. There are several things that we want to try here, including Redshift, RDS, and maybe custom databases or proprietary databases in EC2 that would allow us to scale up and down quickly. Event-driven design. Rather than having scheduled jobs that would kick off at a given time and do a certain task, we would like to switch to kicking off the code based on events. As soon as a file lands on S3, we would like to kick off an EMR cluster that processes the file and does all the processing and puts the data back on S3, rather than having this hourly job or daily job that would wait for a particular hour or day. We would like to use Lambda, and to some extent we already have used it, and it was pretty successful, where as soon as the file lands, a Lambda event kicks off an EMR cluster and does all the processing, puts the data back on S3, and shuts down the EMR cluster. So we have already successfully implemented that partially in the past. And the several other things that we would like to try are automatic code deployments, test automation. Although it's a little tricky to have test automation for data, we are still trying to figure out how to do that, but that's one of the things that we would like to accomplish in the next few months. And to some extent, the data analytics portion, where enabling our analysts to launch an EMR cluster and choose the tool of their choice, like Spark or Impala or Presto, we are already able to achieve that. We have trained our analysts how to use AWS, launch an EMR cluster, read the data that is stored on S3 using Hive, Pig, and Impala and Presto are the next things that are coming in. So we were able to do it already, and like I said, we don't have to have a single Hadoop cluster that does all these things. The analysts can have their own Hadoop cluster. You know, if they want a 100-node Hadoop cluster or a 200-node Hadoop cluster, they could launch their own, run their analysis, and shut it down when they're done. And they can have their code, all the code they ran, saved up so that they could do that again if they ever have to do it again. So